Imagine a single point charge. Its electric field radiates outward in all directions like a tiny glowing star. But what if we stretch that charge out into an infinitely long straight wire? We want to find the electric field at a specific point, a distance r away. A naive approach is to chop the wire into millions of tiny point charges and add up all their individual field vectors. But watch what happens when we pair up charges on opposite sides of our point. The horizontal pushes perfectly cancel each other out, leaving only a vertical push straight away from the wire. Because the wire is infinite, this cancellation happens everywhere, meaning the total electric field must point straight outward, perpendicular to the wire. To calculate this exactly, we first need to know how packed the charges are. We call this the linear charge density, represented by the Greek letter lambda, which simply means the amount of charge per meter of wire. Now, instead of adding up infinite tiny vectors, we can use a physics cheat code, Gauss's law. Gauss's law says if we trap charge inside an imaginary 3D shape, the total amount of field piercing that shape depends only on the charge inside. Pause here and predict what imaginary shape perfectly matches the symmetry of our straight wire. A sphere won't work because the field lines would pierce it at all sorts of messy angles. The perfect shape is a cylinder perfectly centered around the wire. Let's give our imaginary cylinder a radius of r and a length of L. Now we just count the electric flux, the field lines poking through the cylinder's surfaces. Look at the flat circular end caps of the cylinder. Because the electric field points straight outward, the lines skim right past these flat ends without piercing them, meaning zero flux here. All the flux goes through the curved outer wall, where the field lines hit exactly at a 90-degree angle. The area of this curved wall is the circumference 2 pi r times the length L. So the total flux is simply the electric field, E, multiplied by this area. According to Gauss's law, this flux equals the enclosed charge, which is lambda times L divided by the constant epsilon naught. Notice we have the imaginary length L on both sides of our equation. They beautifully cancel out. Rearranging, we get our final elegant formula, E equals lambda over 2 pi epsilon naught r. Unlike a point charge whose field fades by 1 over r squared, the wire's field fades slower by just 1 over r. By finding the right symmetry, an impossibly messy infinite sum turns into a clean, beautiful geometric truth.